Now we have combinations. So combinations occur whenever all selections come from a single group of items. No item may be selected more than once, and the order of arrangement does not matter. So here, picking ABC is the same as picking CBA. So if we make our selections from a group of n items, the number of possible combinations is. We use NCR here, and the formula is the thing we just calculated divided by the number of items we were picking factorial. So what that does is that divides out the number of ways that I can arrange those objects. So if I'm picking 4 things, 4 factorial is the number of ways I could rearrange the 4 things. So I'm going to divide by that so that my number becomes smaller and gives me just how many ways I can grab 4 without caring about the order. So in problems, this will be where they're picking a committee or a board where they don't name the positions. They're just saying, we're going to put 3 people or 5 people or 4 people into this subgroup. How many ways can I do that? So, like literally, this part is the NPR. There's our permutation formula divided by the extra r factorial. So in my head, I'll kind of ask myself, is order mattering here or not? If order doesn't matter, divide by the extra thing. Divide out the ways I can order the things. So here, 8 students, James, Dora, Maria, Leo, Gary, Tyler, Casey, and Henry, are members of the science club. 4 of these students are randomly chosen by drawing names to judge a science fair at a local middle school. So here, it's just 4 judges. We don't care which way we pick them. So what is the probability that James, Maria, Gary, and Tyler are chosen without regard to order? So this is a probability question. So this is actually asking us to figure out how many ways can I do the thing over how many ways is there to do the big thing. So like how many ways can I do my prescribed subset versus how many ways can I pick any subset. So the how many ways can I pick 4 out of 8 is going to be our C formula. We're going to divide by the extra. All right, so this is going to be, let's use a pen. A combination, 8 choose 4. So 8 factorial over 8 minus 4 factorial. That's our normal permutations where the order would matter. But since we're just grabbing a group of judges, we divide by the extra 4 factorial. Now this is not the probability, this is the total number of ways I could pick a 4-person group. So 8 times 7 times 6 times 5 times 4 factorial, but it cancels one of the 4 factorials on the bottom. So then 4 times 3 times 2 times 1. The way these formulas work, everything on the bottom will cancel into something on top. This must work out to be a number, a whole number, not a fraction. So 3 times 2 is 6, so the 6 is gone. 4 goes into 8 twice. So 7 times 5 times 2, which is 70. So there are 70 ways to choose a 4-person judge panel out of 8 total people. So James, Maria, Gary, Tyler. If I'm going to pick that particular subset, that is one subset. because I don't care what order I'm arranging them in. So that's 1 out of the 70 total ways. Now, it's not always 1 on top, but most of our probability problems, it does end up to be 1, except for the double dice that I threw on the test and confused everyone with. Now, what should be part B? What is the probability that James, Maria, Gary, and Tyler are chosen in that order? So again, another probability. I need to know how many ways are there to choose an ordered set of 4. And then this is one precise way I can order that particular subset of people. So that is one of however many ordered sets of 4 there are. So now we have to figure that out, which is what we had, but we're not going to divide by the extra. So that'd be 8 items permuted 4 ways. 8 factorial over 8 minus 4 factorial, which will end up being 8 times 7 times 6 times 5. All right, so calculator. So 1,680. So there are 1,680 ways to pick an ordered group of 4 from 8. There were only 70 when it was unordered. Now this particular arrangement is one way out of that 1,680. Because if I said James, Maria, Tyler, Gary, that is different ordering from James, Maria, Gary, Tyler. So that is one branching on my crazy tree diagram, as it were. So order mattering or not makes a huge difference. How many items we're pulling from also makes a huge difference. So now, ice cream. Suppose you select 3 different flavors of ice cream in a shop that carries 12 flavors. How many flavor combinations are possible? Note that we are not interested in the order in which we pick the flavors. So let's just say we're picking pints of ice cream out of 12. So the order I grab them in doesn't matter. It just matters what 3 I'm walking home with. All right. So order does not matter, means we're going to divide by the extra. So we're doing 12, choose 3. The 12 factorial over 12 minus 3 factorial. And then we're also going to divide by the extra 3 factorial. So I have my ordered sets, and then 3 items can be arranged 3 times 2 times 1, 6 ways. So I could go chocolate, strawberry, vanilla, chocolate, vanilla, strawberry. But when I go home, it don't matter what order I picked them up in. All right, so the 12 minus 3 is 9 factorial. So I only need on top 12 times 11 times 10. And then I have the 3 factorial on the bottom, which the 6 will go into the 12 twice. So we get 22 times 10. 220. So there are 220 flavor combinations by choosing 3 flavors out of 12 total. But this is one of those, like, whether or not order matters sometimes can be difficult to pick up. That's why the note is here to be very obvious about we don't care what the order is. But if I was making like an ice cream cone, which my daughter got an ice cream cone set for her birthday, so it's like cone, and then which one do you want on the bottom, mommy? We got 7 different ice creams and 6 different toppings. That'd make a good test question. And 3 different kinds of bottoms. A cup, of vanilla cone, a chocolate cone. So how many different 5-card poker hands can be dealt from a standard deck of 52 cards? All right, so we have 52 cards, and it just matters that they are different. And for a poker hand, the order you have the cards in does not matter because you can rearrange your cards. So this is I've got my 5 spots. I get my first card. Now there's only 51 left, and then only 50 left, and then only 49 left, and then only 48 left. Order does not matter. It means we're going to divide by the ways I can arrange 5 things. So we're going to divide by 5 factorial, which is 5 times 4 times 3 times 2 times 1, which is 120. So let me crunch the number. So 52 times 51 times 50 times 49 times 8. This is definitely why we tell you to have a calculator. And because it's typed, divided by 120. So 2.6 million roughly. So that's how many different 5-card poker hands. What's the probability of the 5 cards being a royal flush of hearts? So a royal flush of hearts is 1 hand out of the 2.6 million. So that is the probability. Now, if they had just said, what's the probability of a royal flush? There are 4 ways to get a royal flush, 1 in each of the suits. So then I'd have a 4 on top, and then I'd have to reduce. But this is why I don't like card questions, because this is assuming you understand poker and that the order you get the cards in doesn't matter, and that you kind of know what a royal flush is. Like, this is why I don't like card problems. It's too many assumptions. Food, on the other hand, you are in charge of making the food choices to be served on the buffet at a dinner sponsored by a club you are involved in on campus. The catering service offers 8 appetizers, 6 main courses, 4 breads, and 9 desserts. You have been assigned to pick 5 appetizers, 3 main courses, 2 breads, and 4 desserts. In how many ways can you select a buffet? So the first question is, does the order matter? We're putting them on a buffet. So no, it doesn't matter what order I pick my food choices in. So this is all going to be combinations. We're going to divide by the extra. But this is actually going to be several different ones. So we have appetizers. There are 8, and I'm going to choose 5. So I'm going to do some typing here just to keep it a little more organized. The main course, there are 6, and I'm going to choose 3. Then the bread, there are 4, and I'm going to choose just 2. And then dessert, there are 9 lovely ones, but I am only allowed to pick 4 because budgeting sucks. All right. So each of these are going to work out to be a number. So I'm just going to pick random numbers out of my head. So there's like 80 ways to pick the appetizer, like 80 different appetizer selections, and say 60 different main course selections, and however many bread and however many dessert. Once I know that, that's my how many choices I have for the first entry, how many choices I have for the second entry. This is the multiplication principle. We're going to multiply these four numbers after we figure out each one. That's a lot of buffets. This is also where it's nice to have the combination or permutation buttons worked out. I do not, so this one is going to be 8 times 7. No, that takes forever. All right. 8 factorial over 8 minus 5 factorial, which is only 3 factorial, but times 5 factorial. So that gives us 8 times 7 times 6 over 3 times 2 times 1, which gives us 56. So there's 56 appetizer menu selections. Now, 6, change colors. 6 factorial over 6 minus 3 factorial times 3 factorial. 6 times 5 times 4 over 3 times 2 times 1. 20. 20 ways to do the main course selections. Here, let me space this out a little more. All right, so the bread, 4 choose 2. 4 factorial over 4 minus 2 factorial times 2 factorial is 4 times 3 over 2 times 1 is 6. So there's only 6 ways to choose 2 different breads from a list of 4. Which, yeah, there shouldn't be that many. It's a small list, and then we're picking an even smaller. But our desserts. So I wonder, are there more ways to pick the desserts, or were there more ways to pick the appetizers? Well, let's figure it out. So 9 choose 4, 9 minus 4, and then times 4 factorial. So that's going to be 5. So 9 times 8 times 7 times 6. 5 factorial would cancel with the 5 factorial. And then the bottom 4 times 3 times 2 times 1. And as I said, it will always cancel. So 9 times 7 times 2. 9 times 7 is 63. And then times 2 is 126. So yes, there are more ways to pick the desserts than there are to pick the appetizers. I think that more has to do with the out of 9 and out of 8. All right, and now for our final answer, we're going to multiply those 4 numbers. Good Lord, this is ridiculous. So we have 56 times 20 times 6 times 126. So 846,720 ways to pick the buffet. Whew. All right. The last thing talks about probability versus coincidence, which is a little weird, but a kind of interesting thing that you can do with probability.